All right, here we go. Physics video 2.2, honors physics. Now we're going to learn about adding vectors, all right? Learning targets are right here on the screen. So here's the deal. You, at some point, first grade, second grade, something you learned how to add scalars, right? That's a thing that you know how to do. So for example, if I told you that Roy bought 3 apples at one store, and then he went to another store, and he bought 4 apples, and I asked you how many apples he bought, then you'd go, oh, well, he bought 3 apples at the first store, 4 apples at the second store, that's a total of 7 apples, right? Easy peasy, right? Because the apples don't have direction. Just 3 apples, 7 apples, 7 apples. Right? 3 apples plus 4 apples is 7 apples. Okay? But adding vectors is a little bit different because you have to keep track of the direction. So, let me kind of walk you through an example, all right? So in one dimension, it's actually not too different because we keep track of the direction by using just positives and negatives. All right, and in fact, this first example is actually the exact same thing, right? If he walks 3 miles east, and then he goes another 4 miles east, then the total displacement, what is it? Well, let's see, he went 1, 2, 3 miles east, plus another 1, 2, 3, 4 miles east, for a grand total of 7 miles east, right? Okay, so that seems to be the same thing as the apples, right? But the only reason that's true is because our direction is the same. What if he goes in a different direction? What if he goes 1, 2, 3 miles east, and then turns around and goes 4 miles west? 1, 2, 3, 4 miles west, right? Oh, shoot, I wanted that to be red. Because you care. All right, here we go. So we're going to go 1, 2, 3, 4 miles west. All right, and so then the resultant displacement, instead of being 7 like it was in this first example, now the resultant displacement is 1 mile. And in fact, it's -1, right? Because this 4 miles was also negative, right? Okay, so in all 3 of these examples, whether it's 3 apples plus 4 apples equals 7 apples, or 3 miles plus 4 miles equals 7 miles, or 3 miles minus 4 miles equals -1 mile. These are all addition. The only difference is over here, this is scalar addition, and over here, I did vector addition. And you can see that the direction that the vector points in affects the answer, right? Because in both cases over here, we had 3 miles and 4 miles, but we got different answers because in the second case, the 4 miles was west, okay? But even still, this isn't bad because all you got to do is keep track of positives and negatives. All right. So down here, I asked this question: how do you represent it with a drawing? Well, I sort of have already alluded to this, right? That's what this drawing right here is, right? So notice what I did. I took my vector A and I drew it. Okay. Then when I drew my vector B, I began my second vector at the head of the first vector, right? And then I drew it. Okay, so that was the blue vector is vector A, and the red vector is vector B. So that drawing there is A plus B. And then the green vector is my resultant. And the resultant vector always points from the start of your first vector and points towards the end of your last vector. So that's my resultant. So this right here is a graphical drawing of the equation A plus B equals R. Okay? Now, what happens if it's not one dimension, right? This was basically last chapter, right? You've done this before. I'm giving some new fancy terms to it, right? Resultant and all that kind of stuff. But you've done this before, okay? So let's see what happens here. All right? So, oh, actually, I'm sorry, I'm getting ahead of myself. So a couple things to remember when you draw vectors. First of all, the length of your vector represents the magnitude, okay? It's the size of the vector, all right? Obviously, your arrow needs to point in the direction of the motion, okay? And this little paragraph here basically says what I talked about over here, okay? When you add your vectors, you always place, you draw vector A, and then you draw vector B, and you ensure that you place the tail of vector B at the head of vector A. right? This is what is called placing the vectors head to tail, okay? So then when you draw the sum, your resultant, to find your resultant, you draw it from the tail of your first vector to the end of your last vector, okay? So suppose I had this. Suppose I had vector A and I had vector B, and I wanted to mathematically add them. Well, what I would do is I'd say, all right, here's my vector A. It's already on the screen there. To add it to vector B, I would take vector B. That's not what I wanted to happen. That is annoying. Let's try this again. Here's my vector A. Here's my vector B. So if I wanted to literally add vectors A and B, what I would do is I would take my vector B and I would place it so that its tail is at the head of vector A, and then my resultant would be this vector. There's my resultant. Okay? So that is called vector addition. So this is a graphical drawing of A plus B equals R. Okay? Because vector addition is not the same as scalar addition. All right? So how do we do it? Right? Like, this is a graphical drawing. What does it mean, though? All right? So here's a real simple example. So in this example, Roy's going to walk 3 miles east. That's going to be my vector A. And then he's going to turn and walk 4 miles south. That's my vector B. And we want to find his overall displacement. That's my vector R. Vector R. So vector A is 1, 2, 3 miles east. Vector B is 1, nope, sorry, it's supposed to be blue. 1, 2, 3, 4 miles south. That's vector B. This is make it negative if you want, going down. This is 3 miles to the east. So my resultant vector then is this guy. Okay, so now this is what we just finished doing, right? Do the Pythagorean theorem to find the magnitude of R. 3 squared, 4 squared, square root, you all know that gives you 5 miles, right? At, well, we got to find the direction, right? So draw your little compass. Here's east, here's south. This angle is south of east. Find the angle. It turns out to be, what's that, 53 degrees, basically. 53 degrees east. Nope, sorry, south of east. South of east. If I misspoke a minute ago, I apologize. It's because here's east, we are south of it. Okay? So there is my resultant vector. So here's a case where 3 plus 4 is 5, and it's accurate, okay? But technically it's 3 miles east plus 4 miles south is 5 miles at 53 degrees south of east, all right? That's what we're doing here, okay? Now, it can get uglier than this, all right? So suppose Roy walks 3 miles at 40 degrees north of east, and then he turns and goes 4 miles at 20 degrees east of south. Let's find his overall displacement. All right? Well, so graphically, here's what it would look like. So Roy's going to start here, say, arbitrarily, and he's going to walk 3 miles northeast, 40 degrees northeast. So 1, 2, 3 miles. So there's vector A, 3 miles. I made it a little bit too steep. Let's just do this. You ready? Oh, whatever. It's just a scap, so it doesn't matter. My angle's a little too steep. All right. Then he walks 4 miles at 20 degrees east of south. So it's not quite south. It's 20 degrees east of it, and it's 4 miles. So 1, 2, 3, 4 miles. There's my vector B. 4 miles. All right, and we're trying to find his overall displacement. So we're looking for the resultant vector. I'm going to call that R. So this is what I'm trying to find. Okay? So, but this drawing doesn't really help me any, right? Because there's no way I can find out how long this line is or what these angles are, because I just sort of sketched it, right? At my old school, there's a teacher there who used to have people use a protractor and a compass and make drawings, which I think added some value in terms of understanding what this meant, but it didn't help you solve them very efficiently, all right? So here's the process. So here's the process to add vectors mathematically, right? So the first thing you're going to do is you're going to find the components of all of your vectors, okay? All the given vectors, find the components. Then you make a little chart to add the components, and that allows you to find the components of the resultant. Then once you've got the components of the resultant, then you can find the resultant itself. All right? As you're doing this, make sure you keep a few extra significant digits in your work and then round at the end. Please, please, please make a separate triangle for each vector. All right? So let me do a quick example. All right? So suppose I give you this. Suppose I gave you Roy walks, 3 miles. Oh, well, I already gave you the problem, right? So he's going to walk 3 miles at 40 degrees north of east, and then he's going to turn and go 4 miles at 20 degrees east of south, right? And we want to find the resultant displacement, okay? So what we're going to do is we're going to draw a triangle. Excuse me. We're going to draw a triangle for each of these vectors, all right? So let's call this one vector A. We're going to call this one vector B. So here I go. Vector A, 40 degrees north of east. So here's northeast, 40 degrees north of east. Well, here's east. I want 40 degrees north of it. Here's vector A. It's 3 miles. So I want to find my AX and my AY. Okay? So do your trig. I'm going to skip the trig here because I think most of you are fairly comfortable doing that. All right? The way this triangle is set up, I'm going to use cosine to find my AX. It turns out to be 2.30 miles. And I'm going to use sine to find my AY. It turns out to be 1.93 miles. Notice my AX points east, so it is in fact positive. My AY points north, so it's positive. I'm putting those little plus signs so I know I didn't just forget a sign. All right, so that's a triangle for vector A. Let's move it over here. All right, now I'm going to repeat that same process for vector B. Here's my compass. We're going southeast, right? All right, and it's 20 degrees east of south. So here's south, 20 degrees east of south. So this is obviously not drawn to scale. Here's my vector B, it's 4 miles. So now I can close off my triangle, right? And we need to be going south and east. So here's my BX, here's my BY. So I'm going to use trig to find my BX and my BY. This time sine gives me my BX. So that turns out to be 1.37 miles. Cosine will give me my BY. That turns out to be negative 3.76. Again, this is not drawn to scale. All right, so that is step one. I have now found my vector components, right? Okay. Step two, we're going to make a chart. So I've got a couple vectors. I've got vector A, I've got vector B. Each of those vectors has an X and a Y component. So vector A, the X component is positive 2.30, and the Y component is positive 1.93. For vector B, shoot, I wish I'd color-coded these. I'm going to do that because it'll make things a little bit easier here in a minute. All right, so let's see. Our AX was 2.30. Our AY is 1.93. These are all miles. For B, the X component is 1.37, and the Y component is negative 3.76. I'm worried I didn't stress this enough. This needs to be negative because it points down. The math won't tell you that. You have to watch your signs, S-I-G-N signs, well, and your S-I-N-E signs too, I guess. All right, so there's my vectors, all right? So that's step one, find the vector components. Step two, make the chart to find the components of the result. Well, remember, we're adding, right? So to find the components of my result, you literally just add columns. So 2.3 plus 1.37 is 3.67. And over here, 1.93 plus negative 3.76 is negative 1.83. So this is my Rx. This is my Ry. Okay. So now we can find the result. So my resultant is a vector that has a horizontal component of 3.67 and a vertical component of 1.83. So draw it. I always draw the horizontal component first. It doesn't really matter. So here we go. Rx, 3.67. Ry, negative 1.83. Notice head to tail. Here's my R. So now you just do your Pythagorean theorem to find the magnitude of r, 3.67 squared, 1.83 squared, add them, square root it, and you get 4.1 miles. Remember, you always find the angle at your origin. So, didn't let me do it. Smartboard is being really ornery lately. There we go. Here's my origin. I want to find this angle. So, opposite over adjacent, inverse tangent of it. Gives you 26.5 degrees. And then this angle is not east, it is south of east. Okay? Now, if you chose to make your drawing this way, then you get this angle, which would be, 63.5 degrees east of south, also acceptable. All right? So notice, in my setup, I had 3 vectors. Specifically, I had vector A, B, and R. And so to solve the problem, I made 3 drawings. I made a drawing for vector A, I made a drawing for vector B, and I made a drawing for vector R, right? So now let's go back to that graphical representation, all right? Here's what I really just did. Let me do this. I want to pin that page, and then oh no. Here we go. Okay, so remember this drawing from forever ago? This is the same problem, right? Roy walks 3 miles at 40 degrees north of east. 3 miles at 40 degrees north of east, right? And then 4 miles, so it's the same problem, right? So what this chart over here is really doing is this. Get rid of this blue. Undo, undo, undo. There we go. Okay, so what the chart is really doing is this. What we're doing is we're saying, all right, well, horizontally, vector A took me 2.3 miles east. So here's the 2.3 miles. That's my ax, right? And then vector B took me another 1.37 miles east. So there's my bx. Add those together, and it gives you how far my resultant vector went east, right? So it's yellow plus green equals pink. Okay? Then I repeated that same process vertically. Vertically, what happened? Well, I went north 1.93. That's my AY. Then I turned around and went south 3.76. That's my BY. For a total of going south 1.83. All right? So what this chart is basically accomplishing is it is a mathematical representation of this graph that we drew over here. Okay? And you'll notice there are 3 triangles here, right? There's a red one, a blue one, and a green one, which I wish I'd made black. And those correspond to, let me do this. So notice we've got a red triangle that corresponds with this triangle. Those 2 triangles are the same, but just flipped over. Blue triangle, those triangles are the same, but flipped over. Unfortunately, this one isn't to scale. I really should have, it should be more like this. I just didn't do a good job drawing my 20 degrees over here. Okay. And finally, we've got the green one, which corresponds with this black one. Okay? So that is how you do that. All right? So last thing. This process works exactly the same for any kind of vector. Okay? Any kind of vector. It doesn't matter whether it's velocity or displacement or force or momentum or some other crazy thing you haven't heard of. So here's what I want you to do. I want you to try this problem on your own. All right? So you've got a ladybug crawling at 0.36 meters a second at 60 degrees north of west across a conveyor belt. Okay? Then the cashier turns on the conveyor belt, Ladybug keeps walking, but the cashier turns on the conveyor belt, and the conveyor belt is also now moving. So now the ladybug's velocity is going to be the combined result of him walking plus the conveyor belt. Okay, so to solve this problem, what you're going to do is you're going to literally add this vector with this vector and find your result. Okay, so pause the video right now and try to solve it. Okay, I'm going to assume you have now paused and done that. Here is the answer. If you did not get that answer, we'll be going over that at start class when I see you next. And then you can dive into the homework, all right? These problems are tedious, but the cool thing about it is once you know how to do one of them, you can do any of them. They're all exactly the same, okay? So there you go, vectors.